Guys, this is dark and it has a huge mass and it's small. That's 3 smoking guns right there, right, implicating a supermassive black hole. Space can be scary to think about. The dangers that lurk within the vast expanse of space can be terrifying. While this applies to the entire concept of space exploration, the one part that has always been intriguing and terrifying at the same time is black holes. These beasts of power have been the subject of countless research all across the globe. Scientists have been trying to figure out just what black holes really are and what lies within them, but all of that changes now. Neil deGrasse Tyson just revealed something huge. Our black hole is less massive than the one in the center of the Andromeda Galaxy, our nearest big galaxy. So, we have black hole envy, I think we do. We finally see what's inside a black hole and, well, all of it might just blow your mind. So, join us as we take you on this intergalactic journey and answer one of history's most asked questions. What is a black hole? Created from a massive explosion, the black hole's mass is concentrated in an incredibly small region, creating a gravitational force so intense that nothing, not even light, can escape from it. Once something is in there, it's going to stay in there forever. These forces of energy come in various sizes, ranging from stellar black holes, which can be a few times the mass of the Sun, to supermassive ones that exist at the centers of galaxies and can have millions or even billions of times the mass of our Sun. Scientists have observed the effects of black holes indirectly for decades now, and with every piece of data we uncover, hundreds of secrets emerge. Even though it seems like they're so massive and powerful that they can't possibly have an origin story, they do. Black holes don't just exist in space. They're created. They need the remnants of massive stars that have exhausted their nuclear fuel to be born. These stars undergo a supernova explosion, a spectacular event that marks the end of their lives. During a supernova, the outer layers of the star are violently expelled into space, while the core undergoes a gravitational collapse. Not all collapses are the same. If the core's mass is several times larger than that of our Sun, the force of gravity overwhelms all other forces, causing the core to collapse inward. This collapse is so intense that it compresses the mass into an incredibly small volume, creating an object with a gravitational field so powerful that nothing will be able to escape its grasp, thus creating a black hole. The size of a black hole is determined by its mass. Stellar black holes, which are the most commonly known type, have a mass range from a few times to several tens of times that of our Sun. At the core of a black hole lies the singularity, a region of infinite density and spacetime curvature. According to our current understanding of physics, the laws of nature break down at this point, and our conventional theories cannot fully explain what happens within the singularity. To truly understand the nature of singularities, we need to think outside the box. In the world of physics, a singularity refers to a point in spacetime where certain quantities become infinite or undefined. These singularities appear in various theoretical contexts, such as at the beginning of an expanding universe, commonly known as the Big Bang singularity, and within the inside of black holes. When we study the Big Bang singularity, a fundamental challenge arises. According to the theory, the universe originated from an extremely hot and dense state about 13.8 billion years ago. But as we rewind time toward this initial state, the equations of general relativity, which govern the behavior of gravity, break down. This breakdown implies that our current understanding of physics cannot fully describe the conditions at the moment of the Big Bang. Resolving this issue requires a theory that combines general relativity with principles of quantum mechanics. Black holes contain singularities at their cores. These are regions where the gravitational pull becomes infinitely strong and spacetime is highly curved. According to general relativity, matter and energy that fall into a black hole reach its singularity and become infinitely compressed. This concept is beyond our current understanding of physics. Adding to the problem, the challenge of singularities has motivated scientists to search for a theory of quantum gravity, which aims to unify the principles of general relativity and quantum mechanics. Quantum gravity seeks to provide a framework that accounts for the behavior of spacetime on both cosmic and subatomic scales. A theory like this could potentially offer insights into the nature of singularities and how the universe really works. One approach to addressing the issue of singularities is the theory of loop quantum gravity. This theory suggests that at extremely small scales, spacetime is quantized, meaning it consists of discrete, indivisible units. These fundamental units are often referred to as loops or spin networks. In loop quantum gravity, the concept of quantization is applied to spacetime itself. This means that spacetime isn't considered a continuous and infinitely divisible entity but rather a collection of discrete elements. These discrete units of spacetime are often seen as interconnected loops or networks that represent the underlying structure of the fabric of the universe. Within the framework of loop quantum gravity, singularities associated with black holes and the Big Bang could be resolved. One of the key insights of this theory is that at extremely small scales, the discrete nature of spacetime prevents the occurrence of infinite densities and curvatures that give rise to singularities. In classical general relativity, for example, in the context of black holes, loop quantum gravity suggests that as matter collapses toward the core, the spacetime fabric becomes increasingly tiny. This size prevents the matter from reaching an infinitely dense singularity. Instead, the collapsing matter encounters a quantum bounce near the core, where it rebounds and begins to expand again. This scenario leads to the formation of a new spacetime region inside the black hole, often referred to as a quantum black hole or a bounce region. Stellar black holes are the most commonly observed type of black hole in the universe. They are formed through gravitational collapse at the end of a massive star's life. Once a massive star exhausts all its nuclear fuel, the outward pressure generated by nuclear reactions can no longer counteract the force of gravity pulling inward. The gravitational force becomes dominant, causing the star to collapse under its own weight. This collapse results in the formation of a stellar black hole. As the star collapses, it becomes incredibly compact, packing a significant amount of mass into a very small volume. As a result, stellar black holes typically have a mass ranging from a few times to about 20 times that of the Sun. Despite their mass, they have remarkably small sizes. Their diameter is only a few kilometers, which just goes to show how extremely dense they are. The immense density of a stellar black hole leads to the formation of an event horizon, a boundary beyond which nothing, not even light, can escape. This event horizon marks the point of no return, where the gravitational pull of the black hole becomes so strong that any object or information that crosses it is trapped forever within the black hole. Then we've got intermediate mass black holes. While the precise mass range for intermediate mass black holes is still something scientists need to put through more research and refinement, they are generally thought to have masses ranging from thousands to tens of thousands of times that of the Sun. These colossal beasts occupy the central regions of most galaxies, including our own Milky Way. They hold significant gravitational sway over their galactic surroundings and have a profound impact on the evolution of galaxies. The formation of supermassive black holes remains an active area of research and is still not fully understood. But even then, lots of different theories have been proposed to explain their origins. One prominent hypothesis suggests that supermassive black holes evolve from smaller black holes through a process called accretion. According to this idea, as matter such as gas, dust, and stars accumulates around a black hole, it forms a swirling disk known as an accretion disk. The black hole's immense gravitational pull draws material from this disk, causing it to spiral inward and ultimately merge with the black hole. Over vast periods of time, this continuous accretion of matter allows the black hole to grow to a supermassive scale. During the accretion process, enormous amounts of gravitational potential energy are released as the matter falls into the black hole. This released energy powers some of the brightest and most powerful phenomena in the universe. But away from all of that are charged black holes, which represent a fascinating variation of black holes characterized by the presence of an electric charge. There are two main types of charged black holes: Reissner-Nordström black holes and Kerr black holes. Each type exhibits distinct properties that are formed from the relationship between the black hole's charge and other factors such as rotation. Reissner-Nordström black holes are charged but non-rotating. They are described by the Reissner-Nordström solution in the framework of general relativity. The charge of these black holes affects the behavior of their gravitational field. However, in terms of their overall structure, Reissner-Nordström black holes are similar to uncharged black holes. They possess an event horizon, but the size of the event horizon for a Reissner-Nordström black hole depends on both its mass and electric charge. On the other hand, Kerr black holes are charged and rotating. They are described by the Kerr solution in general relativity. The combination of electric charge and rotation introduces unique phenomena associated with these black holes. One of the notable effects is called frame dragging, which occurs because the rotating black hole drags and twists the surrounding spacetime. Kerr black holes have both an event horizon and an inner region known as the Cauchy horizon. This is an inner boundary within the black hole that separates the exterior region from the region where the singularity is located. The presence of electric charge in a black hole creates a repulsive electrostatic force in addition to the gravitational force. This electrostatic force can impact the behavior of particles and matter near the black hole. For example, charged particles may experience repulsion from a black hole's electric charge, affecting their trajectories and dynamics. While charged black holes are a theoretical possibility, they are not widely expected to exist in nature. Most black holes are formed from astrophysical processes that result in neutral objects, meaning that they lack a net electric charge. If a black hole were to acquire an electric charge, it would likely neutralize itself over time by attracting and capturing opposite charges from its surrounding environment. We've heard a lot about black holes, but to actually see one might change everything we know about these entities. With technology becoming more advanced each day, scientists have finally been able to observe and confirm the existence of a black hole. Not just one, though. Two groundbreaking observations have provided us with direct evidence of black holes. The first direct observation of a black hole occurred in April 2019, when the Event Horizon Telescope collaboration captured an image of the supermassive black hole at the center of the galaxy M87. This black hole is located approximately 55 million light-years from Earth. The image, which shows a glowing ring of hot gas surrounding a dark central region, represents the event horizon of the black hole. The observation confirmed the existence of a supermassive black hole and provided unprecedented visual evidence of the black hole's event horizon and surrounding accretion disk. Then came the observations from gravitational wave observatories like LIGO and Virgo. These observatories have detected ripples in spacetime caused by the collision and merger of black holes. The detection of gravitational waves in 2015 marked a monumental breakthrough in astronomy and provided indirect evidence of black holes. These observations confirm the existence of binary black hole systems where two black holes orbit each other and eventually merge, producing powerful gravitational wave signals. And while we're still trying to understand these black holes, maybe even getting lost in them, for now all we know is that black holes are a reality. It's crucial for scientists to continue studying them to better understand their properties, behaviors, and implications for our understanding of the universe. Black holes, despite their enigmatic and fearsome reputation, continue to captivate the imagination of scientists and lay people alike. These cosmic entities, born from the remnants of massive stars, represent the extreme limits of our understanding of gravity and the fundamental laws of physics. As we delve deeper into their mysteries, new questions arise, challenging our current theories and pushing the boundaries of scientific exploration. One of the enduring puzzles surrounding black holes is the phenomenon of Hawking radiation. Proposed by physicist Stephen Hawking in 1974, Hawking radiation suggests that black holes are not entirely black but emit radiation over time. This radiation is theorized to be generated near the event horizon, where quantum effects near the singularity cause particle-antiparticle pairs to separate, with one particle falling into the black hole and the other escaping into space. If confirmed, this concept could have profound implications for our understanding of how black holes interact with their surroundings and eventually evaporate over unimaginably long timescales. Another area of active research is the role of black holes in shaping the evolution of galaxies. Supermassive black holes, found at the centers of most galaxies, including our Milky Way, are thought to play a crucial role in regulating star formation and the growth of galaxies through processes such as accretion and feedback. Material falling into the black hole releases immense amounts of energy, influencing the surrounding gas and dust, impacting the formation of new stars and the dynamics of galactic structures over cosmic timescales. The study of black holes also intersects with fundamental questions in theoretical physics, such as the nature of information and the fate of matter that falls into a black hole. According to classical general relativity, information about the matter that enters a black hole is lost forever as it is seemingly destroyed within the singularity. This poses a profound challenge to the principles of quantum mechanics, which dictate that information must be conserved. Recent advances in theoretical physics, such as the holographic principle and the firewall paradox, have attempted to reconcile these conflicting views. The holographic principle suggests that the information within a black hole may be encoded on its event horizon in a lower-dimensional form, challenging our conventional understanding of how space and information are interconnected. The firewall paradox, on the other hand, proposes that the event horizon of a black hole may be surrounded by a firewall of high-energy particles, which could resolve the issue of information loss but raises new questions about the nature of spacetime near the black hole. Beyond theoretical speculation, observational astronomy continues to provide new insights into the behavior and diversity of black holes across the universe.